Hey folks, we're going to continue from that last discussion, and we'll consider this a new discussion, but it's really an offshoot of the previous one. So we're going to talk about work done by variable forces, something called the integral. Okay. Now this is a case in this class where I have to teach you a little calculus before you've probably hit the topic in calculus. So at the end of the last video, we talked about this weird force that's 2x cubed, the constant being 2 newtons per meter cubed, right? It's F over x cubed. And I asked you, how would we calculate the work done from 1 to 4 meters? And one way to do it, okay, would be to try to estimate this area here, okay? And last year they would have had you, add up, make little triangles and rectangles in here and add up areas, and you'd get a reasonable answer, but it wouldn't be exact. So it turns out there's a way to get an exact answer, okay? So here's the deal. We've talked about derivative, okay, which is the slope of a graph. And the derivative is the following. If you have a function where a function of x such that it's cx to the n, then its derivative, this would be like d function dx or whatever, the derivative of it, you take c times n, okay, x, and then you did n minus 1. So for example, if you had 3x cubed, your derivative would be 9x, okay, that'd be the derivative. All right, so it turns out that that's how you find the slope of a function at any point, okay? Well, to find the area bounded by that function and the x-axis, you do the opposite. It's called the integral, and this is the power rule. So integral power rule, okay? So this only works for polynomials, like x, x cubed plus x squared plus x, with some constants in front. And it's really simple. So if you have a function of x such that it's cx to the n, okay, that's a polynomial, okay, then the integral, and here's how you write the integral sign. It's like a big S, okay, and you write the integral, the function of x is equal to, and you take c times x, and you, instead of subtracting 1 from the exponent, you add 1. So now you have n plus 1 over, and instead of multiplying by that new exponent, you divide by that new exponent, okay? Now, I'm going to add something here, and I'm sorry about this, but I'm going to add something. We're going to put a little dx here, okay? So I'm not going to teach this whole thing to you. This is something your calc teachers are going to teach to you, but I want to explain just for a moment what it is you're doing here. So what you're in essence doing is you're taking a very narrow sliver, and the width of that sliver, we call that dx. It's a very tiny chunk of x. Instead of a delta x, this is so much smaller than that, we call it dx. And then the height of this thing at that point is the function of x at that point. And so what you're in essence doing is you're finding the area of that little trapezoid. That is this part of this, okay? The integral sign, that big looking S thing, it's literally means summation. You're summing, you're adding. So imagine you slice this up into a whole bunch of these little vertical slices, and you find the area of each one, then you add them up, okay? Well, that's what this does. Now, again, I'll let your calculus teacher explain how on earth that works, but suffice it is for us, it works, okay? So, for our example, our function of x is 2x squared, right? So, or 2x cubed. So I'm going to rewrite that. Function of x, our force, is equal to 2x cubed, okay? Here's what I want to do. I want to find the work, okay, from 1 to 4 meters. So what you do is you say that's the integral, the sum of that function of x, 2x cubed times dx. So that's the height times the width of one of these little dudes, okay? And you're going to evaluate this from 1 to 4 meters. So you put your limits, the beginning and end of your shape, on the integral, okay? And then you follow this rule up here. So the exponent's a 3. I've got to add 1 to it. So out front, I still have my 2. And then I have x, instead of to the third, now it's to the fourth. And then I divide by that new exponent divided by 4. And you can simplify that to x to the fourth over 4. Okay. Now, you have to then evaluate this. So we put a bar here. Okay. And you say from 1 to 4. So that literally means this is the beginning value and that's the final value. You plug them in and subtract. Okay. Now, on a side note, a funny little thing, this bar, as far as I know in calculus, doesn't have a name or anything like that. So some of my students have come to know it as the Mashar bar because, you know, it rhymes. So, yeah, so just a reminder to tell you to plug stuff in, okay? All right, so if we plug in 4, okay, 4 cubed, or 4 to the, well, I'm sorry, I lied. This is over 2, sorry. All right, made a math error there. All right, so this would be 4 times 4 is 64 times 4 is, oh, I don't know. It's getting to be a pretty big number, right? So I'll do 4 times 4 times 4 times 4 divided by 2. All right, so I get 128 minus, and then I plug the 1 in. 1 to the fourth over 2 is minus a half. So the exact area of that graph is 127.5. And because we're doing f and x, that's joules, that's work. So the exact area from here to here is 127.5. Okay, so this is a way to figure out an exact area. It's called an integral. Okay, and again, your calculus teachers will tell you more about that and why it works. So what this leads us to is a much more general definition of work. So if I ask you to write down the definition of work, most general form, here's what it looks like. Work is equal to the integral. And instead of using x's, they often will use s's, from S1 to S2. That just means a path. You're moving from point 1 to point 2. The function as a function of s dot ds. Okay. Now a couple things to note. Let's say your work is constant. Let's say it's just your force is constant. Let's say your force is 2 newtons and you pull this thing from 0 to 5 meters. Okay, well, the work is 10 joules, right? Well, this gives this to you. What you have there is you're integrating 2x to the 0 from 0 to 5, okay? So to do our integral, we do 2, we add 1 to the exponent, so 1 over 1, which is just 2x. And you plug in here 0 and 5, you subtract, and you're going to get 10 joules, okay? So it works for constants too. This works every time. That's why it's called the most general definition, okay? So if I were to give you, let's say, a formula quiz or something like that, and I asked you, hey, what's the definition of work, most general definition, this is what you should write down, okay? Now, I got another example to kind of walk through with you just for a second here to get a little practice. Let's say I give you some crazy force, and that force is 2x cubed plus 3x minus 5. And I want to find the work done by that force from 2 to 5 meters, okay? So we're going to use our work, most general definition, so we're going to integrate 2x cubed plus 3x minus 5 dx and evaluate that from 2 to 5, okay? So you're going to use this polynomial rule, okay, on each of the terms. So the first term becomes 2x to the fourth over 4, just like before, okay, plus the next term becomes 3. Now this is x to the 1. So now we're going to make it x to the 2, okay, and then divide by that new exponent, which is 2. And then minus, and 5, it's like 5x to the 0. So that becomes 5x to the 1 over 1, or just 5x, okay? And then you're going to evaluate this thing from 2 to 5 meters, okay? All right, so let's try this out. 5 to the fourth is, oh gosh, it's 125 times 5, 625. So we got 625 over 2, that'll end up being, plus 5 squared, 25, 75 over 2, minus 25 over 1. That's plugging the 5 in, and then minus, and then we got to plug a 2 in, right? So 2 to the 4th, 2 times is 16. Half of that would be 8, plus, let's see, that'd be 6, and then minus 10. Okay. Let's see, 625 plus 75 is 700, so it'll be 350 minus 25. So we have 325 minus 4. So your answer would be 321 joules. That's how much work that force did in moving the object from 2 to 5 meters. Okay, so that's an example of how to use this inverse polynomial rule. Now, one more thing I want to mention about this in springs. Okay, let's say I've got an example like this, the following. Let's say here's a spring, okay, and let's say the equilibrium position for the spring is right here. That's where it's unstretched. So I have compressed the spring. And I put a cart here, you know, let's say there's no friction. We'll call this position A, and let's say this is 5 centimeters from equilibrium. Let's say I'm holding the cart there, and then I drag the cart with the spring attached all the way over to here. We'll call that point B, and let's make this 10 centimeters from our equilibrium position, okay? How much work was done on the spring and by the spring? Okay, so the force in this case is negative kx. That's the force done by the spring. Okay, so that's by the spring. The force done by me would be positive kx. Okay, so now looking back at the picture here, x is negative when we're to the left of equilibrium and positive when we're to the right. So for instance, when this thing is here, the spring is pushing right because it's a negative x and you have a negative in front. So the force is to the right. And then since x is negative, I would actually be pushing left on this thing to hold it in place. You know, you're pushing to the right and you're holding it as you're releasing it toward the left. Okay. So let's first find the work done by me. So that's the positive kx. So the work done by me, and I got to give you K. That might be helpful. Let's say K, make it a simple number. Let's say it's 1,000 newtons per meter. Okay. So the work done by me, okay, would be the integral. And I'm going from negative 0.05 meters, that's your 5 centimeters, to positive 10 centimeters. And I'm integrating Kx, which is 1,000 times x. Okay. And if I figure out the work done by me, oh, and by the way, technically you should times this by dx. You're adding up all these little areas, okay? That's going to become more important later as we go. So you would get 1,000x squared over 2, or 500x squared, and I have to evaluate that from negative 0.05 to positive, and this is 10 centimeters, which should be positive 0.10 meters. So we might want to change that. So 0.10 meters, okay? All right, so if I plug that in, 0.1 squared is 0.01 times 500 would be 5. And then minus, and then this would be a quarter of that, so 1.25. And so you get positive 3.75 joules. So that's how much work I did to move the cart from point A to point B. The work done by the spring, okay, would simply be the exact opposite of that. It'd be negative 3.75 joules. All that would happen here is you would put a negative in front of this 1,000 here, okay? So the work done by you is positive 3.75. Work done by the spring is negative 3.75. Now, another note I'll make. What if we started at 5 centimeters and stopped at 5 centimeters to the right of equilibrium? So we went from negative 5 to positive 5. What would your answer be here? Okay, well, your answer would be 0. In other words, you don't got to do any work to get this thing from here to about here. The spring would do all the work for you. It would push this thing to equilibrium. It'd be moving really fast at equilibrium, and then it would coast to stop it at that point there. So if you put a negative 0.05 and a positive 0.05 here, and you plug them in, you're going to get a 0 work, okay? Now, one last very important note, all right? So I'm going to pause here for emphasis. Very, Very important note, okay? Work is the integral of force as some function of distance or displacement dot ds, okay? These have to be some kind of a position, usually measured in meters, okay? They have to be position. Let me give you an example of a misconception that students will make. Let's say I gave you a force, all right? Let's say I said the force was 3t squared, so 3 times time squared. Some people will say, okay, and let's say I ask you, what's the work done from 1 to 4 seconds or something like that? So a lot of students will go, oh, okay, I'll do my integral 1 to 4, 3t squared. But all of a sudden, do I plug a dx in here? Do I plug a dt in there? That's the first confusing thing. Then they'll do the power rule, like it'll look like this, which just becomes t cubed. Then you would evaluate that from 1 to 4, which would be 4 cubed is, what's 4 cubed? 256, I believe. Let's see, 4 times 4 times 4. Oh, gosh, it's only 64. Okay, so 64 minus 1, and they would write 63 joules. And that would be wrong. That would be a big frowny face. Don't do that, okay? Because your force in this case was not a function of position. It wasn't a function of distance in any way. It was a function of time. Now, it turns out the integral of f dot dt is something else, but it's not work. So when you find work on something, it has to be, okay, the force has to be a function of position, of meters, okay? So like our previous force here was F equals negative kx, or this one here was a function of position. So now you can calculate work that way, okay? If they give you a force as a function of time, you're going to have to find some other way to calculate work. All right, so I hope that was helpful. I know this is a new topic for most of you. If you've never had calculus before, the polynomial rule for integration is very simple. Once you've done it 3 or 4 times, it'll become this lickety-split, no problem at all, okay? All right, so until next time, have a good one.